Hello everyone, good day. In this video, we are going to discuss the concepts of persistent volumes. If you like this video, please subscribe to VSpark's channel and click the bell icon for the latest updates. This is the agenda of this video. We are going to discuss on these topics in this video. What is a persistent volume? A persistent volume is a storage resource in the Kubernetes cluster, just like the worker nodes. Nodes provide the compute power like CPU and memory to our pods, whereas the persistent volumes provide storage capacity to our pods. The underlying storage for the persistent volumes will be provided by the storage providers, or it can be created using the local storage system like NFS, SCSI, etc. Persistent volumes are also referred as PVs. To use a PV resource, it must be requested through a persistent volume claims or PVCs. Pods mount these PVCs as volumes. A PVC is a request for storage which is used to claim a PV, mount the same into the pod. Pods consume node resources like CPU and memory. In the same way, PVCs consume PV resources. Persistent volumes allows data created within the pods to persist beyond the life cycle of a pod. That is, even if the pod is deleted, the pod data stored in the persistent volumes will not be lost. This data will be stored in the underlying storage. Types of persistent volumes. Kubernetes supports several different types of persistent volumes that alter where and how our data is stored. Following are the different types supported by Kubernetes. In a local PV type, data is stored on the local directories of the cluster nodes. Host path volumes type will not work in a multi-node cluster, but it will work only in a single node Kubernetes cluster. In this type, we will be using the local directory as the persistent volume. NFS type provides access to the network file system to create storage volumes within it. iSCSI type provides storage from a iSCSI based environment. FC, that is fiber channel type, provides storage from a fiber channel environment. Apart from these types, there is a category used commonly in today's world, that is CSI type, that is container storage interfaces. CSI type allows integration with storage providers that supports CSI specifications. CSI integrations and its plugins are most commonly supported in cloud platforms. For example, AWS EBS, AWS EFS, GCP's persistent disks, Azure storage, etc. We can use any of these types of storage system to store our data as a persistent volume. Access modes. Volume access modes define how the persistent volume should be mounted in the nodes and the pods. A persistent volume can be mounted on a host in any way supported by the storage service provider. PV support 4 different types of access modes. We will see one by one. First one is read write once. In Kubernetes notations, it is abbreviated shortly as RWO. A PV with read write once access mode will be mounted by a single node with read and write privileges. However, read write once access mode still can allow multiple pods to access the volume when the pods are running on the same node. Second is read only many. In this access mode, the volume can be concurrently mounted to multiple nodes with read only access to the pods. Third mode is read write many. In this access mode, the volume can be concurrently mounted to multiple nodes with read and write access to the pods. Finally, it is the read write once pod mode. In this access mode, the volumes can be mounted by a single pod with read and write access. Use this mode only if we want to ensure that only one pod across the whole cluster can read or write the data to the volume. Even a different pod in the same node cannot access this volume. At a time, only one pod can access this volume. Volume modes. Kubernetes supports two volume modes in persistent volumes. That is, file system mode or block mode. This volume mode is an optional parameter in the YAML definitions. File system is the default mode if the volume mode is not defined. In the file system mode, when requesting a persistent volume from the underlying storage provider, Kubernetes will create a file system within the block device, provided that the device should be empty or it should be a raw device. This will be mounted onto the container file system as a directory. If the block device is already having a file system and some data, Kubernetes will mount the existing file system and the data into the pods directly. Whereas in the case of a block volume mode, the persistent volume from the underlying storage will be presented as a raw device to the pods. The application running in the pods should know the mechanism on how to handle this block device. Ideally, the application should create a file system on top of this device, but it should be done from or within the pod. Now, let us discuss the terminologies used during the life cycle of a persistent volume. Provisioning a persistent volume. There are two ways to provision persistent storage volumes in Kubernetes. That is static provisioning and dynamic provisioning. With static provisioning, the PVs are created well in advance by the cluster administrators manually. That is why static provisioning is also called as manual provisioning. Users claims this PV storage by creating a PVC request. The claimed volumes are then mounted into the pods. In dynamic provisioning, when none of the static PVs are matched with the user's PVC request, Kubernetes cluster will try to automatically provision a storage volume for the PVC request. For example, let's say a pod needs 5 GB of storage, but that is not available in the PV storage pool. So, the pod can request for a 5 GB of storage dynamically using the PVC request. Dynamic provisioning is possible only when we pre-created an entity called storage classes. Storage class creation will be done by the cluster administrators. Along with this administrator, need to enable the default storage class on the API server. Binding. What is a binding? When a user requests for a static PV using PVCs with a specific amount of storage, the control plane watches for a new PVC request and tries to find a matching PV and binds or links them together. This is called as binding. That is associating a PV with its PVC. In the case of dynamic PV provisioning, the dynamically created PV will always be bounded to the requested PVCs. Using or consuming a PV. How to use the provisioned PVs? To use these PVs, pods need to mount the persistent volume claims as volumes. In other words, PVs are consumed by the pods via the PVCs. Reclaiming. When a user or a pod is done with their volume, they can delete the PVC objects that allows reclamation of the PVC resource. The reclaim policy in the PV tells the cluster on what to do with the volume after it has been released from its PVC claim. By default, the reclaim policy is retain. With this retain policy in place, the volume can be reused or reclaimed with another PVC and can be mounted in another pod. In this case, the data created by pod number 1 will still present in the pod number 2. Reclaim policy. Kubernetes supports these reclaim policies, that is, retain, delete, and recycle. With retain policy, cluster will retain the provisioned storage for future usage by releasing the PVs from its PVC claim. With delete policy, cluster will delete the PV object from the Kubernetes cluster as well as the provisioned storage in the external infrastructure. With the recycle policy, cluster will recycle the PVs by emptying its contents and performs a basic scrub on the volume. This makes these volumes available again for a new claim just like a new volume. Status or phases. A persistent volume will be in one of the following phases or states, that is available, bound, released, and failed. A PV will be in available state when it is not yet bounded to a claim, meaning PV is a free resource. A PV will be in bound state when it is associated or bounded with a claim. In released state, claim has been deleted, but the PV and its associated storage is not reclaimed by the cluster. When there is a problem in reclaiming a PV, PV will be in failed state. Well, that's it for this lecture. Thank you from vSparks and thank you for watching this video.